So I thought I would dive into a topic in a little more depth. I'm going to talk about vectorization, and I'm going to try to set the appropriate context for it, of whether you should worry about it or not. In general, it's getting pretty hard to ignore, but I think it's surprised a few people at Intel that work on our hardware side how much it's been ignored, but I think I can explain that. But we'll talk about it. So I'm going to talk about vectorization mostly. It's funny. Parallelism to me is very intuitive. This is a great example. You've got a nice highway. You probably won't line up all the cars. We use parallelism in our everyday life all the time. So I think some people are really afraid of parallel programming. Probably not in this room, but I think about, if you saw this on the highway and you're driving, I can't imagine there's anyone out there that wouldn't think of pulling their car into one of those other lanes, right? So this is kind of what vectorization is about, as a form of parallelization, or any parallelism is this. It's like, let's use all the resources available to us. So I want to, I talked about how important essentially data parallelism is. That was the Amdahl versus Gustafsson thing, the idea if you can scale your problem up. In fact, when we were preparing the structured parallel programming book, my co-authors, Michael McCool, used to be a professor at University of Waterloo and started a company called RapidMind that Intel acquired. He lives in Japan now, hence the Japanese cranes on the front of our book, which disappeared on the Japanese translation of the book, which I don't understand. We still don't understand that. But Michael McCool started a company, RapidMind, focused on data parallelism for different devices. Arch Robson's the architect of TBB, and I put the book together. And at one point, if you did the pre-reading, one of the chapters I included in the pre-reading was the intro chapter from the TBB book, which I wrote in 2007. And I talk about task parallelism and data parallelism. It's a pretty common thing if you're going to teach parallelism. Teach that there are two types of parallelism, task parallelism and data parallelism. Of course there are, and I did that in the TBB book. When I got ready to write the intro chapter for structured parallel programming, I showed up to my two co-authors and said, there's no such thing as task parallelism. And they said, what are you talking about? You wrote about it. I said, it doesn't matter. I think all the time I've ever tried teaching task parallelism, I've wasted, because all the parallelism needs to be in the data. And that's a little extreme too, but the parallelism's in your data, and that's the weak scaling, strong scaling. The weak scaling, which is the type of scaling you're going to get most often, comes from data parallelism. So if I had to give you advice, don't go looking for task and data parallelism. Go look for data parallelism. You can come back around. And data parallelism, by the way, often is best taken care of by decomposing onto multiple cores or threads. But I'm going to focus on vectorization. And I'll just say the point of my talk for the next half hour or 40 minutes is going to be, we really need to embrace explicit vectorization. And I'll try to make the case for this and explain why, and turn up the contrast a little bit about what people have actually been doing and why we should all want to pull our hair out. And some people have over this problem. But let me start. All of you are working on some things, so I want to take a quick poll. How many people in the room think you've done something to try to make your code vectorize? That's, I don't know, maybe a third of the room is saying that they did. That's higher than I usually get. Which is interesting. And if I had one of our architects of the CPU here, they would just be falling on the floor, even though I tell them, people don't use this as much as they should. We spend a lot of effort on it, and why is that? Well, I'll tell you why. SSE could get you a 2x performance increase, and SSE, AVX can get you 4, and we can get you 8x on double precision now with the 512-bit wide, or 16 on us. I'd say that 2 and 4x speedups is boring. And because at the same time, we've been scaling up the number of cores on a device and the number of CPUs in a cluster has been growing much faster. And this little icing on the cake to get a 2x maximum, guaranteed not to exceed on SSE, it's just not worth most people's time. Now, some people have gotten great results with it, don't get me wrong, but now that we're inching up into the 8 and 16x category, it's time to look at it again. And guess what? The tools and the languages aren't up for what we want to do with it. So some people say, can't we just solve this? Can't the compiler just do it for me automatically and so on? And the answer is no. And I'll try to make a case for that. Of course, should you just ignore it? I think don't ignore vectorization. So again, go back to the architects of our CPUs at Intel. They would say that the SIMD instructions we've added to the instruction set should make things go faster. In fact, wow, if you if you move from SSE to AVX 512, we should be able to quadruple the performance. So this is, my point here is the hardware has taken the vectorization we used to give you with SSE, and we've upped it. Instead of being able to do 2 double precisions at a time, we can do 8 now. That's a 4x boost in what the hardware is offering to you on a cycle-by-cycle basis. That's trying to help, it should be compelling for wanting to take another look at vectorization if you haven't in the past. On the other hand, why are we really doing it? It's because of Moore's law. We've got all these transistors sitting around. We've got to do something with them. And this seems to work pretty well for a lot of applications. And we've seen great speedups in moving. So what speedups can you expect? This is just a graph showing with SSE some of the SIMD speedups we were able to see on a machine, and this one's with 6 cores with hyperthreading. So this is supposed to be kind of a real-world sense. I can throw around a lot of numbers and say, well, SSE can get you 2x, and the cores can get you this, and so on. But quite often we see that we can hit problems and see 3 to 4x speedups when using vectorization versus not vectorizing code. But we're all in good company here. I have not got a copy of this book yet. I did get a text from my 18-year-old daughter who's traveling right now going, oh my God, Dad, I didn't know you had How to Train Your Dragon and Monsters, Inc. people on the front of your next book. My co-authors work for companies like DreamWorks and Pixar, and we did a SIGGRAPH tutorial last year, and then we turned it into a book this year, and none of my co-authors use vectorization. They'll talk to you about how great TBB is. They'll talk to you about how to do parallelization. They'll talk to you what they're doing in animation and why the movies are better and how you train your dragon gets better effects. And Ronald got an Academy Award this year, a Technical Academy Award for his work on software that he talks about in Chapter 5, all of that. And none of my co-authors use vectorization, none of them. They said, we mean to look at that. Well, why? Because parallelism's much more, the parallelization using something like OpenMP to do task or TBB is much more compelling than vectorization. So I'm going to talk to you about how to do vectorization, but if you're thinking about parallelization versus vectorization, parallelize first. We're going to give you more cores and going to keep scaling up the size of HPC machines, and you've got all that available to you. Vectorization's a nice icing on the cake. Let me make sure I didn't lose anyone. Vectors are incredibly simple, what a vector is. A vector of numbers, that's what I mean by vectors. It's just a list of numbers. One of the side effects of vectors is that vectors, to work well on architecture, should be sequentially placed in memory. So memory location 0, 1, 2, 3. That's the assumption here, and that means we can pick them up in chunks. And if we want to do a vector addition, this is what vector add means. Pairwise addition. And when I talk about vector instructions doing multiplication, they do pairwise multiplication. If you take the middle line, the 1.7 times the 0.8, we get a 1.36 result. The only thing happening multiplication-wise is two numbers being multiplied and then placed adjacently. The power of these instructions is that they can pick up a chunk of this vector at a time. In the case of AVX 512, if these are single precision numbers, it could pick up 16 of them, actually more numbers than I have on the screen. It could pick up 16 of them of one vector, 16 of the other, multiply them together and get a result out, all in parallel. Now the question is, how do I take a program that I've already written or a program I want to write and take advantage of vectorization? You might have a program like this. It wants to add two vectors together and have an output. And here you go. And what you actually wrote, I like to call this a serial trap. You know, a for loop is actually a serial construct. It doesn't say you can do these in parallel. So the compiler has to assume that there might be overlaps. So the loop says, you know, go fetch me A sub I, fetch me B sub I, add them together, store them to C sub I, increment my index and go back. That's what you actually wrote in C that you wanted to have happen. If it vectorizes, when we say vectorize, what we want to do, instead of loading one thing at a time, we want to load 4 things at a time into a register that can hold 4 things at a time, add 4 things at a time, and store 4 things at a time. That's what vectorization is. That's what you want a compiler to do. Vectorizing this loop means taking the thing on the right, and instead of emitting this code, emit that code. But I want to remind you that's not what you wrote. What you wrote was do them one at a time. And so the problem is the compiler needs to think about whether doing 4 at a time would be the same. And there's nothing that says that max needs to be divisible by 4. And unfortunately, there's nothing that says that these items don't overlap each other in memory. In fact, there's a famous operating system that until recently had a mem copy that looked like we should speed it up using vectorization, but we have to double check that they don't overlap because someone cleverly decided that mem copy is so fast that they put a 0 in the first element and then told it to copy the first element to the second and do that byte-wise to zero out memory. And of course, if you did that in parallel, it wouldn't work so well. Pain in the butt. So this loop is not legal to automatically vectorize. And this frustrates programmers to no end who often tell me that our compiler is stupid. And I say, well, the problem really is the programming language. Ultimately, the programming language doesn't let you say what you want to say. You want to say, do this frickin' thing in parallel, vectorize it. So you have a few choices. Choice 1, hope that the compiler auto-vectorizes it. Throw a switch and say, vectorize what you can, compiler. Now, usually, what a compiler should do is only vectorize it if it's still going to get the same answer. And there have been benchmarking compilers in existence that throw hope to the wind and just vectorize everything. But I think you'll find that any of the compilers you use these days will only vectorize things that it believes will still get the right answer. But you threw the switch and you hope that it vectorizes it. Well, it turns out in that particular loop it won't. The next thing you can do is you can realize, all right, the compiler needs some help. So I'm going to give it some hints. And the C99, and this is supported in most C++ compilers nowadays too, has this thing called restrict, which says this variable, this pointer is not allowed to point to anything that's pointed to by another pointer. And then this can magically vectorize, because the thing we were worried about was that C, A, and B overlapped somehow. The restrict keyword, another way to explain the restrict keyword is, in 1999, the C standard finally offered the capability that Fortran's had since 1956. because Fortran, it's illegal to alias parameters always. And every Fortran compiler in existence will vectorize the equivalent Fortran loop because you don't have to write this silly little word restrict in every parameter in your Fortran program. But C's trying to catch up. The other thing you can do, and this has been around a while, is you can put in a pragma. Most compilers support something like this, IV depth. Again, we're giving the compiler a hint because the language isn't quite meeting our needs. So this is the second thing we could have done with this loop to get it to vectorize. And IV depth means ignore implicit loop carried dependencies. And I'm a compiler guy by training. I managed compiler groups, I studied in college. I love compilers. I seem to like a lot of things, but compilers I really am into. And this makes perfect sense to me, but it horrifies me, the idea that the way we're going to get a compiler to vectorize something is for you as programmers to understand why the compiler didn't vectorize it and then give it a hint in the language of the compiler writers to get around this. And by the way, what the heck does ignore loop carried dependence have to do with the source code? All it has to do with it is that the compiler has decided that there's potentially a dependence between iterations, and you're telling it to ignore it. Now, that's actually pretty dangerous. You're telling it to ignore things that might or might not be ignorable. But that's good. You've helped the compiler do what you wanted. IV depth varies what compilers do with it, but it usually means implied loop carried dependencies. So the compiler might decide it wasn't implied, that it was explicit dependency, and then ignore IV depth and still not vectorize it. I don't have an example that shows that, but it happens. So we have people who put IV depth in front of it, still doesn't vectorize, they're pulling their hair out, and we go, oh, well, you don't want to vectorize this because of X, Y, Z. And the compiler knows better than you. So we finally came up with this idea. And I actually was really opposed to this, but this has been a fantastic success with users. Mandatory vectorization. Let's see, I probably shouldn't curse. It'll be on videotape forever. So this means vectorize this, darn it. Just do it all the time. I don't care what your excuse is. You must issue vector instructions here. Now, of course, the compiler has to actually know how to do vector instructions, but if it does, this says do it all the time. Now, we supported this as Pragma SIMD in the Intel compiler for a while, but it's been added to OpenMP, starting with 4.0, and the syntax is Pragma OMP SIMD. It's available in C and Fortran with compilers that support 4.0, like GCC and the Intel compiler, and I'm pretty sure IBM has it now, but it's a matter of timing. But this says vectorize the loop. I don't care why you think it shouldn't vectorize, just do it. And it sort of extends the language because it's saying that I, as a programmer, have thought this through and I understand the implications of vectorization. Now, if you get that wrong, you may get wrong results. In this particular case, if you pass in data that overlaps, you won't get the same result. But it's your fault because you wrote a program that said ignore it. So there's a lot of different ways you can do this. You could do it on a function basis as well. You can say that this function should operate in parallel using vectors. You could do array operations. One of the extensions in Silk Plus is the concept of arrays. Fortran 90 arrays should do this, but they don't usually because the Fortran standard increases the number of temporaries in most compilers. But either using Fortran 90 or Silk Plus, ideally you could do vectors, arithmetic this way, and this would imply vectorization. It doesn't work in practice between a lot of compilers. It works pretty darn well with the Intel compiler, but it takes a lot of compiler technology to make this work, and I don't think it's a great way to try to code an application if you want it to be portable, even though technically it'll work pretty well with the Intel compiler. Maybe it'll catch on in time. We'll see what GCC can do with it. It's in GCC 4.9. GCC folks think they can make this go, and I think that may change my mind about whether to recommend it. So I kind of gave 3 choices: auto vectorization, just tell the compiler vectorize what you can. Of course, I gave up on that. The next thing you could do is give hints to the compiler to get it over its anxiety, whatever's causing it anxious. The problem is that's kind of an iterative battle. You add a pragma and you see if it vectorizes. And if it doesn't, you go back and look at the reports, find out what's bothering the compiler today. You try to add another pragma to get it over that anxiety. And it's a back and forth. And the problem is the next version of the compiler may have a new anxiety, or the Intel compiler may be happy and vectorize it, and then the IBM compiler doesn't, or vice versa. I think there's a lot of reason to pull your hair out over this. And then this idea of explicit vectorization, which is to tell you that you need to code it and just tell the compiler vectorize it no matter what, I think is a very powerful concept.
How do I know if it vectorized it?
I'll show you some reports. Most compilers can dump a report out to show you what it vectorized and didn't. And then one of the things that's in the OpenMP standard is, I think it's called assert, right? You can do pragma OMP SIMD assert. And if you put that in front of a loop and it doesn't vectorize, it'll cause a compile time error. And so the reason that's really cool is if you work really hard and you get it vectorizing, and you want it to stay vectorizing, you don't want to look at the report every day to see if it's still vectorizing today, you can put that in front of the loop, and if someone changes the code and it stops vectorizing, or they change the compiler, you'll be told right away. And maybe you can debug that. Now, you can get into a whole debate, how good does it have to vectorize? And that's up to the compiler. Our compiler thinks it knows the difference between when it vectorizes and doesn't, but you might be able to create an argument. If you want to know if it vectorizes, hopefully it runs faster, but the direct way to do it is to look at a vectorization report, a dump from the compiler. It can tell you. Or you could just put a pragma OMP SIMD assert in front of it, and it'll do a compile time error if it didn't vectorize it. But a lot of people like to add the pragma SIMD asserts ahead of loops that they've carefully handcrafted, and they're afraid that someone will break it in the future.
How do you choose when you shouldn't vectorize?
When it slows down things? That's a great question. It's very hard. It's, in general, I'd like to believe that you can restructure anything to use vectorization. I mean, that's doing enough data processing, and that vectorization is always useful. But in general, if you have an algorithm that you can rearrange and get to vectorize, it's always a good idea to vectorize, I think. On the other hand, can I tell you that an algorithm that uses OpenMP task plus vectorization will beat another algorithm? I can't give good advice on that. I can't think of an example of where anyone's ever vectorized something and gotten a speed up where it was a bad decision to do that. So I would think always go after it if you can. But I have seen people try to get code vectorized and cause other problems, not be able to get a speed up, and that's a bad idea. So explicit parallelization. So explicit parallelization comes in a few forms. The OpenMP, pragma, SIMD, the Silk plus array notations, or the SIMD instruction intrinsics. And so I really want to stress that I think if you're doing vectorization these days, I would look at these. And that's kind of sad because a lot of people want the compiler to just be magic and do the work for them. Oh, by the way, magic libraries that just vectorize for you, those are always good. So Intel's implementation of BLAS and FFTW and so forth use vectorization. You know, NVIDIA's got their CUDA libraries. Anybody that will do the vectorization for you in a library, go for it. See prior talk where I said, try library first. But if you're explicitly coding, I think I would just give up on the compiler doing it automatically for you as a technique. Now, if you want, throw the switch. If it speeds up, why would you refuse it? But if you want to write code that's portable and stays vectorizing and ports across a lot of different architectures, the best strategy here is to write code in these deficient languages like C or even Fortran and explicitly give the compiler orders to vectorize it. I think that's the best strategy given the languages we have today and likely to be for quite some time. I think writing stuff hard-coded in intrinsics, if you've ever done that, is a bad idea, because if you hard-coded all your stuff using SSE, you probably thought about rewriting it for AVX, which is 256 bits wide, and then you know what Intel comes up with AVX 512. You have to rewrite it again because you hard-code the width. The techniques I'm going after is to keep you writing the code in a natural way, but to think about the implications of vectorization enough and order the compiler to vectorize it, but independent of width. So the examples I've shown so far with the pragmas and all the examples I'll show here, the compiler can be smart enough to vectorize it for SSE, AVX, AVX 512, AMD 3D now, if anyone cares, and you know, what other vector instructions people come up with. I go to the SIMD. So this is the SIMD. This is the SIMD construct. I think I've already shown. Oh, so I wanted to show that the SIMD can be a little more complex. So the OpenMP explicit parallelization, you can often just say OMP SIMD, and that orders the compiler to vectorize it. But you can also do some of the common things, like vectorization. You may have a reduction going on. And in this case, we're doing a reduction. We're summing to a single variable. And this will throw all sorts of red flags for the compiler because it doesn't want to rearrange the order you do the sums in. That may actually matter to you. So a good compiler will not vectorize this unless it gets a sense that you want to do a reduction, meaning that you understand that the additions may happen in different orders. You may add these four numbers and these four numbers and add the sums of them instead of add the first two and then the second two. And you need to understand the implications of that as well. You know, if you have an array of numbers randomly arranged and add them together, you'll get a different answer than if you sort them from largest to smallest. Just the reality of life. So OpenMP committee said, hey, we can let the users write down and tell the compiler that it knows there's a reduction going on here and it still wants it vectorized. And to comprehend this. Now, in this example, the examples I give, it looks pretty darn simple. You would think a compiler could do this automatically, and our compiler can. I would say IBM's and PGI's probably can too. GCC maybe. So, you know, but if you do it explicitly, the hope is that every compiler will do it. And there's all sorts of other things. This is out of the OpenMP spec. You've got safe length, how big of a vector can we do before we run into problems. Some algorithms actually have a maximum vector length that they're safe at. There may be a dependency, but it might be, you know, 8 apart or 100 apart, and you can specify that. And then there are other things about privates and reductions. I'm not going to dive into trying to explain all of these. Probably the most important one here is collapse. You can actually, sometimes you want to write your code multiply nested, but you'll find that the compiler will only vectorize the innermost loop. Usually compilers will do parallelism at the outermost loop, vectorization the innermost. But what if you have 2 or 3 loops nested, quite often 2 nestings, and you want it to vectorize both of them together? Compilers often miss that, or don't vectorize, or they vectorize the innermost loop. And so what some people do is they rewrite their code so the innermost loop does the work that they really wanted to write as 2 loops. And this code is really hard to maintain and understand. But I've seen people do this, rewrite a doubly nested loop to singly nested so it'll vectorize. The collapse directive, you would put ahead of, say, 2 nestings, and you would say collapse 2, and it will collapse 2 loops together and then vectorize them together. And then your code stays looking very nice. So I think here collapse is probably one of the more important ones. Some of these others look familiar. Private variables and reductions can be very useful. And then you can also apply this to functions. So if you've ever written in CUDA or OpenCL, the concept of a kernel function can be very powerful. And this is essentially OpenMP's version of a kernel function. You write a function that operates on one piece of data, but you put this in front of it. You say declare SIMD construct in front of the function. And when the compiler encounters that function being used, it will try to use a vector version of it. So what our compiler does, if you have a function that, like that last one I was looking at, where I was copying well, actually, I could have written it to copy just one data element. If I did that, then I can have the compiler produce vector versions of it, ones that operate at 4 and 8 elements at a time. And then when I call the function, instead of calling it 4 or 8 times, I call it once, and it does 4 or 8 times the amount of data. And this is what allows it. You essentially say, this is a function that operates on one piece of data at a time, but I want you to create vector versions of it. Very powerful feature. Again, this is oriented towards trying to make it so you can write your code in an intelligible fashion, the way you wanted to write it, but you can still get it to vectorize. And then you can also, in the same vein, you may have a loop that vectorization, a classic problem is, I have a loop, it's processing a lot of data. I'm on a multi-core machine with vector instructions. Do I want it to run on multiple cores, or do I want it to vectorize using vector instructions? And the answer is yes, I want them both. And this is what was added to the OpenMP language to specify that. You say that you have you do an OpenMP4, but you can put a SIMD clause on it, and it says, I want you to first spread it out among the cores, but then don't stop there. I want you to vectorize what runs on the cores. I want to get both types of parallelism, but I don't want to have to break this loop into 2 loops. Again, something that a lot of code has done. A lot of people have taken a loop and broken it up to iterate over the cores, and in the middle of that, put a loop to try to vectorize on a core. Sorry, we let everyone down by not having these things in the language sooner. But the good news is it's there now. So Pragma OpenMP for SIMD solves the problem of doing parallelism, task-level parallelism, and vectorization on the same loop. You can combine this with collapse and get really powerful things. So you can collapse a couple of loops, tell it to spread it across the cores, and to parallelize it. So all of this, I focused on OpenMP because I think it's providing the best solution today to explicit parallelization. And if you like directives, or if you can live with them, just use it. If you don't like directives, you're not alone. And in the latest Intel compilers, version 15, we have keyword-based approaches to this. I'm not encouraging you to use these in production code, but if you're really frustrated by this concept, if you want to watch how languages evolve, the C++ committee is very interested in this. And we're leading an effort in it. And we've implemented this in our compiler, and we have some users looking at it. And the question is, can we give more of a program, an API, a function-level API, to cause the same things to happen instead of directives? Directives will never make it into the C standard or the C++ standard. And so we're trying to do something that resembles keywords more, or attributes, to give the compiler the same directives, but not to use pragmas. In any case, we'll see. The next C++ standard 2017, I very much doubt will have this in it, but it'll be considered maybe 2021, since they're on a 5-year cadence. But something to look for. Pragmas may not be the only thing we have in the future, but today they're the best. Now let me review a little history. It's an architecture track, so let's talk architecture. So back in 1997, we added MMX, Multimedia Extensions, except that's not what it stands for. It's 57 new instructions, dancing bunny guys, all sorts of things. Everybody had to have an MMX, a processor with MMX. It was pretty amusing. One of the things that enabled are soft modems. If you ever think about it, we used to have modem cards and modem add-ins, and nobody does that anymore. It's mostly handled by the CPU because of MMX instructions. Finally, in '98, we added floating point. This was supposed to be 3 years apart, but MMX was late. The floating point came a year later, and then we kept adding to it. And we added 57 instructions for MMX, 70 more for SSE, 144 more when we had SSE2, SSE3, SSE3, and then 4.1 and 4.2 SSE. More and more and more and more instructions operating on floating point, doing more packed integer. There's stuff in here for XML. There's pop counts. Anybody know what pop counts are good for? Yeah, that's what they do. They count how many bits are on or off in a given number. Kind of a weird instruction. I could tell you some of the key customers for it, but I'd have to shoot you. There are people who are really interested in this that do interesting things. It's used in cryptography a lot. Cryptographic algorithms, which is, if you're going to be handling a lot of data in parallel, you might as well do cryptographic stuff. AVX bumped us up to 256 bits. The Xeon Phi has a coprocessor version of 512-bit instructions. They're really source compatible with AVX 512, but they're not binary compatible. And there are particular reasons for that, but the AVX 512 will merge the instruction sets. We don't have a name for what we did on Ivy Bridge, so I called it AVX 1.5, and nobody's stopped me yet. And AVX 2 adds FMA. But anyways, you see this, and then AVX 512, I got to introduce it to the world last July for Xeon Phi for Knight's Landing, and then I just published a blog about 3 weeks ago announcing some extensions that'll show up in Xeon, but I didn't say which Xeon processor yet. So we see increasing bit width. We see that it doesn't apply just to integers. We do floating point, single. We're all the way up to 16 wide, single precision, 8 wide, double precision. But here's a fun graph. So I kept saying how many instructions. I took off the names of the processors because it doesn't really matter. And as we go across these, if we had, say, just randomly, it was a Westmere and then a Sandy Bridge and then an Ivy Bridge and then a Haswell and maybe even a future Xeon Phi. If you take a look, this is how many how many instructions the processor adds. Now, this is hard. Good luck going and adding an instruction and deciding how many vector instructions, how many scalar. I picked a method and added them. The trend is really clear. Most of the growth in the instruction set is happening in vector instructions. There's enormous effort going on. And part of the reason is that we found ways to add instructions that make it easier for a compiler to vectorize code. We have some things called collision detection instructions that actually let the compiler vectorize something that might actually be a problem, but detect it in flight and detect the collision, and it'll run a little slower, but it'll still run faster than the serial code would have, even when there's collisions present. So since it's the architecture track, this is probably the key slide. Trend. Intel is mostly investing in adding vector instructions if you were to try to count how many instructions go in our new processors. We are not alone. I don't have graphs for other vendors, but the other vendors of CPUs would have very similar graphs. And I mentioned collision detection. It's a pretty cool new capability for the compiler. If you're doing like a histogram, you could potentially be trying to increment the same index. You're trying to increment, you're doing a histogram, and we actually have a solution for that. There's an instruction added starting in Knight's Landing that allows the compiler to issue vector instructions, and at runtime we detect the collision, but we do it in a way, if you're trying to do 16 wide, we will provide feedback. The instruction will say there was a collision starting in element 6. It'll do the first 5 elements, and there's a feedback so that the loop actually only increments by 6 and tries again with a vector of 16 more. And it might detect a collision this time at element 10. It goes ahead and does 9 elements, increments by 9, and iterates. So we can vectorize loops that are very interesting. So, you know, I encourage you to look at vector reports in any compiler. I'm going to skip past talking in any detail about the Intel compiler today, but it'll be in my slides if you really have time for that. But most compilers have different switches to dump out information, more information you ever wanted. The Intel compiler, we've put a lot of effort into these reports because a lot of people want to understand their vectorization. But final motivation, this ads probably doesn't quite click as well as it did with a group of Fortran programmers I talked to a while back, but there used to be this line of cars called Oldsmobile, and they tried to revive it in the 80s with the tagline, "It's not your father's Oldsmobile." So I want to tell you that vectorization today is not your father's vectorization. This is the seminal article announcing the Cray 1 and communications of ACM talking about Cray 1 actually said that the Cray compiler could vectorize. This is back in 1978. Haven't we solved it? They had it solved then. Now, it was actually funny. It was, which issue was that? That was the January issue. The October issue announced the arrival of Fortran 77. So they were talking about vectorizing Fortran 66 loops. And this is the type of loop that used to get us excited that we could vectorize. This is Livermore loop number 1. And if you didn't vectorize this in a vectorizing compiler, you were stupid. So, and this actually has an IV depth in it to tell the compiler. But it's gotten much messier today. You could have some code that has else statements in it, whiles, make a function call, do all sorts of stuff. I could spend an hour kind of tracing through this. The code can have function calls, conditionals, conditional calls, and you can put a pragma OpenMP SIMD in front of this, and it will vectorize. And actually, we have several real-world examples that are just this messy. This is part of what made us give up on having the compiler automatically vectorize, because the compiler can't really figure out if we vectorize this whether the overhead is going to make it faster or slower, or whether there'll be collisions and so on. But if the user says, I want you to vectorize this, fine, we do it. And if it speeds up, you're brilliant for having told the compiler to do that. Compiler, you can never count on a compiler doing this. But anyways, I skip, not harp on this particular example so much, but we've seen things like Mandelbrot's. This is a little toy example, but where you can declare a function to be SIMD, and then you can have the loop be SIMD, and this all vectorizes. This code will vectorize using our compiler, and hopefully any compiler implementing OpenMP 4.0. And getting some pretty nice speed ups, including in this case on a Xeon Phi with 244 threads using the 512-bit wide vectors. But it really requires that you think a little about vectorization, put these in. The good news is you probably don't have to change your code because of the collapse directive and the SIMD on the parallel 4. You just need to sprinkle some SIMDs around in your OpenMP. In any case, there's a little flavor, a little push for vectorization. Given that we're able to do 16 single precision floating points in parallel, the I think it's rather compelling to pay some attention to vectorization. If you can arrange the processing of data in such a way that you could have 16 floating point computations happening close to each other, and you could sprinkle in a pragma OpenMP SIMD in front of it, you're likely to get a vectorization result out of that and some speed up. But parallelize your program first. So Jackson's going to throw his computer up here, and we'll keep rolling without a break. But I can take a question or two while we go there. Yes?
I have two questions, if it's possible. When you do auto-vectorization, how does the compiler deal with the extra iteration space? Does it just do scalar?
Sorry, how does it deal with what space?
To the closest divisible number by your vector unit, it's vectorizing those, and the extra iteration.
Oh, yeah. Yeah, that's a great question. So the question is, I told it to vectorize. You've got 16 wide. How does it deal with loops that aren't 16 wide? Well, the old-fashioned technique is to run the loop as many times as you can and then have a cleanup loop. That's what most compilers, what we have to do. The problem with that is that now you've increased your pressure on the iCache, amount of code you create and all that drives compiler writers nuts. We have, in the newer versions of instruction set, starting with AVX, they have masking. And what the compiler actually does now is run it one more iteration than you think would be possible, but then use some mask bits to cause the operations not to happen after, so you pick up 16, but you're only supposed to do 5. We set the first 5 masks to 1 and the next to 0. And then those math operations don't happen and the write back doesn't happen. I'll give you a little bug. In Knight's Corner, we pay attention to the mask bits for writing back, but we don't pay attention to them on the math. Oops. So you can get math exceptions on data you didn't want to run. Actually we fixed that. I'm sorry, that was on a prototype. We fixed the math because we had to fix that, but we will still cause a page fault on a write back if it wasn't aligned. Your performance would be terrible if you actually had code that did this because we don't handle alignment as well as we will on Knight's Landing. But the idea is now that you produce one loop but use these mask bits, and generally the compiler might even start using the mask bits at the beginning and the end to get better alignment too.
And also for the performance issues in Sandy Bridge, I think you have 2 load ports of 16 bytes each, right? In order to compensate for the fact that you need a 32-byte load. So basically, with vectorization, the compute is in 1 clock cycle, but actually your load times, you have a penalty there.
Yeah, different architecture. It's one of the engineering trade-offs. It's not fundamental to the instruction set, but one of the trade-offs is how many ports do you put here and there, and those can become bottlenecks. I'd say on Knight's Landing, on Haswell, there are more ports for the SIMD than there had been on the architectures before it, and we'll continue to get feedback from people of how well that's working with real-world codes and see if we should invest in more ports. It's a trade-off. More ports cost power, die area, but yes. Anyways, the feedback was that there are a limited number of ports like on Sandy Bridge, and that loads and stores don't necessarily happen in one cycle, and that's true.